discussing section 7.2 volume. Remember that Friday we have a quiz. Which is quiz 4, I think, and it'll be covering section 7.1 and 7.2. All right, so first intro and basics, very basic and very sketchy, so read the book for these. But the volume of a cylinder is, well, you have to think about what a cylinder means in math. You probably think of a cylinder as like a can of soup, which is a particular kind of cylinder. It's a right circular cylinder. But in general, the base of a cylinder can be any shape. And so a cylinder can be that shape, and then, sort of raised up to make this kind of shape. And so if we have base area that's A and the height that's H, then the volume of the cylinder is A times H, whatever that is. Now, more general shape, so for instance, a blob of some sort. Anybody ever see the Bean in Chicago? Oh, yeah. All right, so, what do you do with something like this? Well, one thing you can do is you can slice it up. You've got to be careful to not do this, not get arrested, but you slice up the thing into, and we don't know what these slices look like. They could be discs, they could be weird shapes, but the slice has, well, it depends on the value of x. So you imagine this thing floating in space, and you slice it in perpendicular to the x-axis, and this slice has area that depends on x. And so the volume is going to be obtained by an integral. You integrate the area of those slices. So you integrate the function a of x. And this integral is going to start at one extreme of your shape, of your solid, and end at the other. So it's going to be an integral from some a to b. All right, now there are some famous examples that you have learned and probably live in a little bit of terror of because you don't know if you're going to remember them. And if you don't remember them, then you're stuck. But as of this week, you'll have a way of producing these formulas. So if you don't remember them, you can just brew them up. So suppose I have a sphere of radius r. Who remembers what the volume for that is? Raise your hand if you know. Really? Come on, somebody's got it. Yeah.
Is it like 4/3 pi squared?
You got it. You can't say like though. Is it like that or is it that?
4/3 pi squared.
Are you sure?
No.
4/3 pi r cubed.
Oh, right. Yeah, 4/3 pi r cubed. V equals 4/3 pi r cubed. It's got to be a cube because it's volume. A right circular cone. So here we got something that has a circle as its base, and it has height h and has radius little r. Who remembers what that volume is? Annika?
Third pi r cubed? Pi r squared. 1/3 pi r squared.
Come on, peanut gallery, help us. Annika said 1/3 pi r squared times h. So it's not the cylinder. The cylinder would be the area of the base times the height. It's 1/3 of that. What about a pyramid? Now, most of you are probably used to thinking of pyramids as, you know, things with a square base, but in fact they can have wacky bases. Here is a wacky shape, and then I'm going to just pick a point that's not on that shape and then draw lines to those vertices. There's my pyramid. What's the volume of a pyramid? Ethan, you look like you know.
I do not know.
So I will tell you that the base has area A, and this thing has height h. Kinsey?
It's 1/3 area times height.
So it's the same thing. It's not the area of the base times the height. It's 1/3 of that. So really, a cone is kind of an example of a pyramid. So 1/3 the area of the base times the height. Now, I'm not going to do these. This is 7.2, example 1. The second one is 7.2, exercise 31. And then the pyramid is book's example 8, so section 7.2. And it's also homework number 35. Now, so the fact that I'm not going to cover it in class doesn't mean that it's not important. It just means that the book does it. The book does those well. So I want, you know, as always, well, you'll see when you get your exams back. One of the exam problems was exactly a book example, as I've always promised. At least one of the problems on quizzes and exams is going to be just like a book example. So read the book and study these examples. Okay, so that was part 1. Part 2 is what are called solids of rotation. So, example 1. Find the volume of the solid obtained by rotating the region. So I have to describe the region. The region is bounded by the curves. So I have to give you a list of curves. Y equals x squared, y equals 0, x equals 1, x equals 3 by rotating that region around the x-axis. I'm going to make some room here. I want to find volume of solid obtained by. So I'm going to have a name for this example, and I'm going to come and put it in later. All right, well, the general approach we're going to have all day today is going to be the same thing. I find it helpful to always, well, you know, I'm a hedgehog. I always do the same approach. So I draw the region. So y equals x squared. Y equals 0 is the x-axis. And then we have x equals 1 and x equals 3. Those are vertical lines. So there's our region. And then I indicate on this drawing how it's going to be spun. I'm going to spin this around the x-axis. Now I keep that drawing and I don't mess with that drawing. Because what I'm going to try to do now is draw the solid, and I'm probably going to screw this up, or you might. So, you know, my advice is make a nice drawing of your region and don't mess with it. Make another drawing of the region. So when I spin this around the x-axis, I'm going to have that version of the curve, but then I'm going to have an upside down version of the curve. And then if I want to convey the solid, well, I just kind of fake it. And I would encourage you to practice this drawing skill, because it's just kind of fun. How do you convey that you've got this thing spun? Well, I draw an oval there. So it's kind of a bugle. And then I want to draw a slice. Now, a slice is going to be obtained by, you know, go back to the drawing of the region, draw a segment that's going to become a radial segment of a slice. So there's that segment, and that's going to spin and give us a slice like that. So region, solid, and then a slice. What's the slice going to look like? Well, it's going to be a disk. Now, what is that radius? Well, that radius comes from here. Where'd that come from? Well, that came from here. What's that length? Raise your hand if you can help me with that. Marcy?
X squared.
Yeah, so r equals x squared. So the area of the slice is going to be pi r squared, so pi x squared squared, so pi x to the 4th. So our volume is going to be the integral from 1 to 3. Oh, because, and I should convey that this starts at x equals 1. And it ends over here at x equals 3. So I'm integrating only from 1 to 3 of pi x to the 4th. So my volume is going to be pi x to the 5th over 5 from 1 to 3, evaluated from 1 to 3. So that's going to be pi over 5 times 3 to the 5th minus 1 to the 5th. 3 to the 5th is 243. So this is pi to the 5th times 243 minus 1. So in other words, the volume is 242 pi over 1. That's our first example of a solid. And it's what's called a solid of rotation, a solid maybe I should say solid revolution. 242 over 5. Pi over 5. All right. Example 2. Find, I'm going to leave space for a title there. Find volume of solid obtained by rotating the region bounded by curves y equals x squared and y equals x cubed about the x-axis. All right, so notice that I don't have as many curves. Here I had x equals 1, x equals 3. Those ended up telling me the endpoints of my integration. So this one's a little bit mysterious. But I'm going to take the same approach. So I'm going to draw the region. Well, I have to start by drawing my graphs. Here's y equals x squared. And then here's y equals x cubed. What are the points where these graphs cross? What are the coordinates? Chase?
0 and...
Oh, xy coordinates.
1.
Wait.
1, 1.
Yeah, so 1, 1. And the other one? Somebody else? What's this? 0, 0. Okay. So apparently my region is this shaded. And I have to convey that I'm spinning that around the x-axis. So there's my drawing of the region. And then the next thing is I try to fake a drawing of the solid. So really it's just going to be that crescent, that little sliver. So I'm going to start by just drawing the region again. But then I draw the upside down version of that. So that's going to go through 1, -1, and it's going to be this kind of thing. And then I have to convey that I have spun it. Well, so I'm going to draw my ovals. So it's kind of a bugle. But then I need to draw a slice. Well, let's see. When I slice that when I slice through this y equals x squared graph is going to give me a circle, and the green y equals x cubed graph is also going to give me a circle. So the green circle is going to be sitting inside of that red circle. And so this, remember what I said about not messing up your original drawing of your region, because these attempts at drawing solids can get pretty humbling. You might make something that's terrible, and you want to have your original region graph not messed up. But there's my slice. So let's draw a picture of the slice. Well, it looks like this. It's this stuff. And notice, well, how do you find the area of that slice? Trent? Yeah, so what does that end up looking like? So it's the outer circle, the outer disk minus the inner disk. So pi r2 squared minus pi r1 squared. So pi times the quantity r2 squared minus r1 squared. Oh, so we're going to need the radii. So here's my r2. It's that red segment. And here's my r1. It's this green segment. So let's go back to see where those came from. Well, that red segment goes from the x-axis up to that y equals x squared graph, and the green segment goes from the x-axis up to that y equals x cubed graph. So over here on this graph, this is going to be my r2. And so that's going to be x squared. Whereas my inner radius, my r1, is going to be down here. It's going to be x cubed. So I'm going to have the area being pi x squared minus x cubed squared. So pi times the quantity x to the fourth minus x to the sixth. Oh, shoot, I erased that one. So the title for this one is rotating around the x-axis, integrating x, and the slices are what are called washers. So that shape that I just drew is a washer. So the previous example, remember I said there was going to come back and put a title. The previous example was rotating around the x-axis, integrating x, but the slices were disks. So you can go back and add that title to example one. Example one was an example where the slices were disks. So our volume is going to be, well, the integral from 0 to 1 of the area of the slice. So the integral from 0 to 1 of pi x to the fourth minus x to the sixth. So that integral is going to be pi x to the fifth over 5 minus x to the seventh over 7. That's all got to be in parentheses, integrated from 0 to, evaluated from 0 to 1. So that's going to be pi times 1/5 minus 1/7. So that's 7/35 minus 5/35. So 2 pi over 35. All right. I know you thought things could not get any more fun, but here's where they get even more fun. So example 3, same region, but spun around the y-axis. So I've already got the region drawn. It's here. Now I just have to convey what it looks like when I rotate it. Well, I'm going to draw, so here's the solid. So I first draw my curves. And then I draw a mirror image of that across the axis of rotation. And then I just fake it and draw circles that sort of convey the fact that this has been spun. So notice that this y equals x squared graph that had been on the outside of the spinning, and so I had colored it red. When I rotate this around the y-axis, that y equals x squared graph ends up being on the inside. And it's the y equals x cubed graph that's on the outside. And so the green graph spins, gives me a circle, and I convey something that's on the back side of a shape with a dotted line. And then that red graph gives me a circle. There's the front of it. The back side of it is dotted. And then if I wanted to shade this to give me my slice looks like this. Again, these drawings are not always successful. So my slice has an outer radius, it has an inner radius. The outer radius is R2, the inner radius is R1. So where did those come from? Well, go back to this drawing. This is y equals x cubed. So there's that inner radius, or that outer radius. And then this green graph is y equals x squared. And so it's that green radius is there. But the thing is, these slices are, they depend, the size of the slice depends on the value of y. This is the slice at height y. So we're going to be integrating y. So rotating around the y-axis, integrating y, not x. So I need to have radii that are expressed in terms of y, not x. So if that's the equation for that red segment, expressed as y as a function of x, how do you express x as a function of y? Because the length of this green segment, of this red segment, that's x. So what is x? Ooh, was your hand going up? Yeah.
X is the cube root of y.
Yeah, so x is y to the 1/3. And what about for the green segment? X equals y to the 1/2. So the slice has area that depends on y, and it's going to be pi times r2 squared minus r1 squared. So that's going to be pi times r2 is y to the 1/3. That's going to be squared. And then r1 is y to the 1/2. That's got to be squared. So this is going to be pi times y to the 2/3 minus y. So that's the area of a slice. So the volume of the solid, so this is the area of the slice. The volume of the solid is going to be that thing integrated from 0 to 1. And I'm going to remind the reader that this is y equals 0 to y equals 1. So this is going to be pi y to the 2/3 minus y, all that in parentheses. So when I integrate, well, I do the power rule, I get, what's 2/3 plus 1? Too slow, 5/3. So pi y to the 5/3 divided by 5/3 minus y squared over 2, and I got to evaluate that from 0 to 1. Well, when I plug in 0, all those terms become 0. So all I really need to do is plug in 1. So I'm going to have pi. Now, dividing by 5/3 is the same as multiplying by 3/5. 3/5 times 1 to the 5/3 minus 1 squared over 2. So that's pi 3/5 minus 1/2. Okay, so that's 6/10 minus 5/10. So 1/10. So pi over 10. Isn't that cool? Yes, it's cool. All right, so that region spun around the x-axis, gave us a volume of 2 pi over 35, but that same region spun around the y-axis gave us a different volume, pi over 10. Example 4. Same region, but rotated around the line y equals 2. So I'm going to draw the region again, just because I'm going to need more space. So there's my there's that. And then, but then I need to be able to draw the line y equals 2 to convey that I'm rotating it around that. So that's the region. We draw the solid. So here's, it gets a little tricky. I'm going to try to get by without drawing the x-axis. Here's y equals 2. And this region is below that. So it goes through 0, 0, and it goes through 1, 1. And I've got that graph, and I've got that graph. So this is y equals x cubed. This is y equals x squared. So then I'm going to have the mirror image of that. So if this is 0, 0, and this is 0, 2, then this is going to be 0, 4. And the mirror image of that point across that axis of rotation is going to be at 1, 3. And so I'm going to have this graph and this graph. And now I've got to convey that this thing got spun. So I'm going to draw a little oval there and a little oval here. The backside of it is hidden because it's behind the solid. So it's kind of a beehive sort of thing. And then I need to somehow convey a slice. Well, I'm going to draw the outer graph in red. And it spins to give me a red circle. And the inner graph I'm going to draw in green. and it spins to give me a green circle. And so then my slice is there. So region, solid, slice. Slice is going to be a washer again. So I'm going to have an outer radius that I'm going to color red. I'm going to have an inner radius that I'm going to color green. And my area of the slice is going to be pi times the quantity R2 squared minus R1 squared. So it's going to be a slice. Now, is this a slice at X or a slice at Y? Marcy?
At X.
It's at X because we're slicing perpendicular to the x-axis. So the slice at x has area A that's a function of x. It's going to be pi times R2 squared minus R1 squared. Okay, so what's R2? Trent? Not quite. Because that would be this length. So you got to go back to your drawing of the solid. Draw in that radial segment. That's going to be this length. Now go back to the region and put that length on here. What's the length of that red line? Somebody from row 2. What's the length of that red segment? Top of the red segment touches the line y equals 2. The bottom of the segment touches the line y equals x cubed. So what's the length of that segment? Yeah, exactly. It's that height minus that height. So R2 is 2 minus, say it again? 2 minus x cubed. And what about the green radius, R1? Well, that's going to be here, a segment whose top endpoint is on the line y equals 2 and whose bottom endpoint is on the line y equals x squared. So the length of that green line is just the difference of those y coordinates, 2 minus x squared. Okay, so my area of the slice becomes two minus x cubed squared minus the quantity 2 minus x squared. Well, that's going to be a mess. So pi times 4 minus 4x cubed plus x to the 6th minus the quantity 4 minus 4x squared plus x to the 4th. Holy cow. So when I simplify this, notice the 4's get together and have a party, and they cancel each other out. So I end up with x to the 6th minus x to the 4th minus 4x cubed and plus 4x squared. That's my area of a slice, all that stuff with a pi in front. So my volume is going to be the integral from 0 to 1 of that mess. So when I integrate that, I get a pi, and I get x to the 7th over 7 minus x to the 5th over 5. I get a wonderful just plain old x to the 4th, and then I get 4x cubed over 3. And I have to evaluate that from 0 to 1. This is not as bad as it looks. So pi times 1/7 minus 1/5 minus 1 plus 4/3. And that ends up being 29 pi over 35. Okay. Sharks and jets and new kids. So 3 groups. Sharks, come over here to the board. You sharks are very quiet. I can't even hear you moving. So volume obtained by rotating the region bounded by Oh, Gabriel, I guess you can turn off the camera now. Well, I'll write down the problems, and then you can turn off the camera. So bounded by y equals 1 over x equals 1, x equals 7, rotating it around the x-axis. Okay, so sharks, there you go. They even give you an eraser. Jets, here's yours. So the region is bounded by y equals 1 over square root of x equals 1, x equals 7, and then rotated around the x-axis. Do you all even know what the sharks and the jets are? All right. Do you even know what the new kids in the block are? All right. So new kids, here's yours. All right, you all need to come up to the board. This sitting on your butt portion of the lecture is over.